This was just a small test, but in reality, smoking causes wildfires in forests, causing massive fires, countless animal losses, and the destruction of their habitats. Hello everyone. Today we have a brand new project called Forest Guard. Forest Guard is basically a end-to-end IoT solution where we have multiple nodes and then a central gateway. These nodes are capable of sensing environmental parameters, wildfires, and detecting gunshots. This can then send their data to a central gateway, which then can sync the same data to the cloud. The challenge in forest area is to make communication between one device to another. In these areas, the cellular network often fails and it's very difficult to lay the data line across the forest. To solve this problem, we are going to use LoRa networking. LoRa is basically like transferring data from one point to another in range of kilometer to few hundred kilometers, depending upon the antenna that we use. And on top of LoRa, we are going to use the popular firmware called Meshtastic. Meshtastic allows us to create a mesh of local network. Let's see how the Meshtastic works. Let's assume we have two devices, a node and a gateway, in the distance of 2 kilometers. But the range of individual LoRa module is only 1 kilometer. So in that case, node fails to send the data to gateway. But with the help of Meshtastic, we can introduce a third device which can communicate between the node 1 and the gateway, transferring the data successfully. This is all because of Meshtastic. In Meshtastic, messages can hop from one device to another until it reaches the final destination. The node is basically a transmitter with few sensors like environmental sensor, smoke sensor for detecting wildfires, and a microphone. Microphone? Yes, we have trained a edge impulse audio classification model and deployed on the edge. This classification model classifies the surrounding sound and the gunshot. With the help of edge impulse model, we can actually detect the gunshots on edge. That's the power of edge impulse to create small classification models for small microcontrollers like ESP32. Then coming to gateway, gateway is basically a device with LoRa and Wi-Fi connectivity with a display. Whatever the data that is broadcasted by the nodes will be received by the gateway, it will be displayed on its screen, and the same data will be pushed to the cloud using Wi-Fi internet. Now, on top of this data, I have built a dashboard which can actually displays all the parameters of individual nodes. Here if you see, I am using Google Firebase as the cloud database, and on top of this data I have this dashboard which shows the registered nodes in this system. Here as of today I have two nodes registered in this system, and out of these two nodes one of them is active, and here you can also see the last updated time with the date. In this card, we'll see if there are any events that had occurred in the past 12 hours. On this map view, all the nodes mapped with respect to its location data. We can have a quick glance of the node's data by clicking on the node. If I go to view details, I'll be navigated to the node's dashboard where we can see the last scene of that node, the location data, number of data points, current environmental condition, historical charts for the environmental parameters, and logs of events. Events like fire and the gunshot with the time of occurrence. Similarly, you can see for the node 2, here we have the same events logged on this. To start with the build, first I have designed the schematic for our node PCB. I am not an expert in PCB designing, so I simply copied the generic ESP32S3 board layout. In this schematic, as you can see, we have a ESP32S3 module. Then we have a USB Type-C for charging and for programming the ESP32. We have the battery management circuit, the battery charging circuit. Then I have added this WS2812B RGB mini LED for the feedback. And finally, I have extended the ESP32 pins to connect to multiple sensors and the LoRa module. I then made a layout of a PCB and arranged all the components in that boundary of the PCB and routed all the connections. If we see the 3D view, here we can see the ESP32S3 module with the type C for charging and programming the ESP32, the feedback RGB LED, the battery management circuit, the charging circuit, a power on and off switch with boot and reset button. And then we have the pads to connect our LoRa module, the smoke sensor, I2C microphone, and the DF robot environmental sensor. On the back, it's flat, there are no components. So once the PCB is designed, I then ordered my PCB through Next PCB. I ordered 5 PCBs from Next PCB. Two of them were assembled, so all the assembly components came pre-soldered through Next PCB's PCBA service. We only need to solder the modules. As you can see, the PCB and PCBA quality is very impressive. As the first module, we have a DF robot's environmental sensor, a GNSS module with its antenna, a MEMS I2C microphone, a MEMS smoke sensor, a Waveshare RP2040 LoRa module with the antenna and Type-C programming adapter, a 70 by 70 solar panel, a LiPo battery. We designed the enclosure for the node in Autodesk Fusion 360 by importing the PCB layout and the available components. And once designed, we 3D printed all the parts in our Bamboo Lab P1S. For the enclosure, we have a housing part, a diffuser part which diffuses the on PCB RGB feedback LED. And finally, we have the cover on which we will glue the solar panel. As the first step of assembly, we need to solder all the modules on the PCB. The environmental sensor, the smoke sensor, the I2C microphone, and the LoRa module. After soldering, make sure to check the continuity of all the connections using a multimeter. Connect two wires to the PCB, which we will connect later to the solar panel. Connect the antenna followed by the battery to the PCB. On the housing, glue the diffuser and a piece of plastic for the light in. Now assemble the PCB into the housing. Screw the antenna onto the housing. Glue the solar panel on the cover. Mount the GNSS sensor onto the cover using 4 screws. Take a 4-pin connector that came with the GNSS sensor, cut it into half, connect the connector to the sensor and solder the other end to the PCB. Also connect the solar panel. Now assemble the housing and the cover part together. In order to flash the firmware in our node, first we need to train the edge impulse audio classification model to classify surrounding audio and the gunshots. For that, I'll open my browser, go to edgeimpulse.com, log in with my account. Once we are logged in, we'll create a new project. I'll name my project as Forest Guard, create a new project. Once the project is created, we need to collect the data. But the challenge with ESP32 is we cannot directly capture the data into our Edge Impulse project. The generic method of collecting data with ESP32 is attaching a SD card module to our ESP32, then capturing the audio files into SD card, then transferring those audio files from SD card to our PC, and then uploading those audio files into the Edge Impulse project. This is a long process. Most of the ESP32s doesn't have the direct SD card support. To solve this problem, I have written a Python Flask app which takes the raw audio data from the UART, converts it to the audio file, and uploads it to the Edge Impulse project using Edge Impulse project API key. To capture the audio, first go to the Forest Guard GitHub repository, then download this repository as a zip file. I have already downloaded it and extracted it. I'll go to this folder. Here, go to Edge Impulse Data Tool, ESP32 Audio Serial, and open this code in the Arduino IDE. So once you have opened the code, make sure to install Fast LED library. So I am using the library version 3.10.3, and also make sure that you have installed ESP32 Board Manager. If you don't know how to install ESP32 Board Manager, you can check the article in the description below. So once that is done, I'll select the board type as DF Robot Firebeetle 2 ESP32S3 since I am following the Firebeetle pin layout in our node. Then select the USB COM port. Here you also make sure that you have enabled the USB CDC on boot and then click on upload. Once the code is uploaded, we will run the Flask application and try to capture few audio samples. For that, I'll go back to the folder, Edge Impulse Data Tool. I'll copy this path. Then I'll open my command prompt. I will navigate to that folder and I will run the app.py code. So this is the command to run that Python code. Once our app is running, I'll go back to my browser and I'll type this URL and it will open us this dashboard to capture the audio data. So here I'll select the COM port. For the API key, I'll go to Edge Impulse project, keys, and here you'll find the API key for your project. I'll just copy it and I will paste it over here. You can select where to upload the data, either in testing or training dataset. Here I'll enter the label name and I'll select audio as the data type. In my data acquisition page, as you can see, till now we don't have any data. So I'll just click on capture and upload and my LED is green. That means it is listening to me and now it has stopped listening. So this is the data that was uploaded from my Flask app using the Edge Impulse project API key. Now similarly, I will start capturing the surrounding sound, that is noise, and then I'll play the gunshot audio in my mobile phone and record them as gunshot with the label gun. Since I don't have like access to gun and like we are not allowed in our country, I'm just playing the gunshot audio in my mobile phone and I'll be capturing the same in our Edge Impulse project. So similarly, I will capture around 120 seconds of noise data and 120 seconds of gun data and make sure that you maintain the ratio of 80 to 20% in between training and test data. Once we have captured around 3 to 4 minutes of data, we'll find all these 10 seconds audio files in our Edge Impulse projects. I'll click on these three dots and I'll click on split samples. So this will automatically split your audio files into small 1 second audio clips. Here you need to make sure that you are cropping the exact features of that audio. Like here you can see this spikes resembles the gunshot. So I am trying to crop these spikes in our audio frames. And I click on split. Similarly for the noise, I'll split the audio samples again. For the noise, you can randomly pick the audio frames. And I'll click on split. In my original project, as you can see, I have captured around 3 minutes of data. I have split the data into training and test in the ratio 80 is to 20. Now we have captured all the data that we require for the classification. We'll create a impulse. So go to create impulse. Here we need to add the processing block and the learning block. Under the time series data, just keep the settings same. I'll click on processing block and I will select audio MFCC. Under learning block, I'll select classification and just click on save impulse. Once your impulse is saved, you can go to MFCC. Here keep all the things same. Go to bottom and click on save parameters. And once we are on next page, we'll click on generate features. Once the features are generated, you can see the clear differences between the noise data and the gun data. Now go to classifier, keep all these parameters same, scroll down and click on save and train. Our classification model has been trained now. So you can see here the score of this model is 96%, which is considered very good. The gunshots can be classified with 94% accuracy. The noise can be classified with 100% accuracy, which is like pretty good. To deploy this into our node, we'll go to deployment, select the deployment option as Arduino library. Just keep all the settings same and click on build. Once the library is built, the library will be downloaded automatically. Now I'll go back to my GitHub folder. Here I'll open Arduino codes and in Arduino codes, select the node version 2. Open in my Arduino IDE. Once the code is open, we'll go to sketch, include libraries, add zip library, and I'll select the downloaded Arduino library from the Edge Impulse. Once you have imported the library, you can just change this name to the name that you have provided. In my case, this is same. After this, you need to install few libraries, Adafruit, NeoPixel. I'll just copy this, go to library manager, and I'll search for this library. We need to just install this. Similarly, I'll install GNSS and environmental sensor library. For that, you need to download the library zip file and import it as add zip libraries, similar to the Edge Impulse library that we have done. In this code, you need to provide the node ID. Here I have put the node ID as 01. You can make it 02, N01, node 01 or something like that. And same will be replicated on the gateway and on the database. That's on the dashboard as well, right? Then we have this GNSS available flag, which is set to true. This means the GNSS module is connected to our node. If you don't want to opt for GNSS, you can just make this false. But in that case, you need to manually set your location coordinates over here. And that's it. Like these are the only two settings that you need to do. Then you can just select the board type as Firebase ESP32S3. Select the COM port and just click on upload the code. This will take some time, but once the code is uploaded, your node will start breathing blue on boot. It will try to connect to the gateway. To build the gateway, you can just follow this in-depth step-by-step guide of the forest guard. Here I have not only showed how to build the node, but also in-depth instructions on how we can build the gateway. If you follow this documentation, you should be able to make one of the gateway by yourself and also the node. In this article, I have not only shown the step-by-step instructions but also provided all the things required like how to get the electronic components, the Gerber files for the PCBs, the CAD design files, how to 3D print them, how to assemble them, how to flash the firmware, and how to configure the dashboard for the Forest Guard project. The link to this step-by-step article will be provided in the video description. Once you have built the gateway, just connect it to your PC. Go to the same GitHub folder that we have downloaded and open the gateway version 1 code in our Arduino IDE. In this code, you need to make sure that you have installed all these libraries. Then provide your Wi-Fi credentials, that is your Wi-Fi name and Wi-Fi password. Then we also need to provide our Google Firebase credentials. For that, go to your browser, go to console.firebase.google.com and here click on create a new Firebase project. Name your project and click on continue. Once your Firebase project is created, go to the project, go to build, real-time database, create a new database. I'll set up this database in test mode and click on enable. This had created your real-time database. I'll just copy this URL and I'll go back to my sketch and paste the URL over here. You need to paste the URL in this format. Once that is done, go back to your Firebase project, click on project overview, click on add app and then click on web. Here I'll name my web app. These credentials will allow me to connect the Firebase to my web dashboard. I'll just copy all these credentials and save it for later. I'll click on continue to console. Go to project overview and project settings. On secret accounts, database secrets, copy this secret key by clicking on show and copy. Once I copy this, I'll go back to my sketch and I will paste the database secret over here. Once that is done, I'll select my board type as Arduino Uno R4 with the USB COM port. And finally, I'll upload the code. For the dashboard, I used Lovable.dev to develop this app. In this dashboard, you can go to the configuration settings. Here you need to provide the Firebase configuration that we have copied earlier. To find them again, you can go to the Firebase project, project overviews, project settings. Here you have the same configurations for the Firebase. You can just copy paste the same over here and click on test and save configuration. Once that is done, you can go back to the dashboard. As of now, as you can see, I have two nodes registered in this system, but both of them are offline. So I'll just turn my node on. Starts with blue breath and it is trying to communicate to gateway for the registration. Once it is confirmed, it glows in green color whenever it sends the data to the gateway. Once the gateway receives the data, it syncs the same data on the cloud, and as you can see, our node is online, right? And it's real time. So similarly, when there happens any event under like 12 hours, it will show the event numbers over here. I'll try to create a fake event, which is the same gunshot event. And as you can see, it's started red. Here my node has detected the gunshot. The event is then triggered on the gateway, so it started beeping, and the same event is replicated on our dashboard. If you see our dashboard, on the node, you can see there is a gunshot event with 94% accuracy, and if I go to view details, it had logged the gunshot event with the time and the date. So this is how the events get logged in our database. I hope you like this project. If so, make sure to hit that like button, share this project and subscribe to our channel. Thank you.